Hi, in this video, we will go through the steps involved in downloading a model which will be for position control of the DC motor using an proportional and integral controller. On the right hand side of the model, you see the mathematical description of the mechanical setup of the hardware. On the left hand side, that is the control algorithm for the DC motor. So let me start from this one. So this is a velocity actuator which is representing a DC motor output. The output of the DC motor, the mechanical part, has a spring damper constants, a friction model, and a transmission which represent a gearbox attached with a bearing. The feedback is taken from the bearing to an encoder model which represent an encoder which will convert the counts or the revolutions into number of counts, and it will give a revolution output. If we go inside the model, you can see the number of counts is 40,080. So this will be given as a feedback to the controller. The controller will process this output, and the output of the controller is given to an gain block, and this is the gain of the DC motor. So this indicates the gain offered by the DC motor constant. So if you have a different DC motor, you have to adjust the gain to give an actual velocity output of the DC motor. Inside the controller block, we have a motion profile which gives the position output in form of some motion. So if you open it, I have set to an pulse output. So the position of the motor will go up and down or the backwards to its original position. So I'm only using the position output. So the start time would be 1 second. The stop time is 3, so that will be define the rise time. This is the return time. So it will start from here and end at 7 seconds. The stroke defines the total position taken by the motor. So if you take 1, so it will be 1 revolution. So the output of this is given to a plus minus block. So it is being subtracted from the feedback coming from the motor. So as we are getting a feedback from here, so it is again divided by 40,000 number of counts and given to this plus minus block. This output would be treated as an error output, which in turn provided to PI controller, and the output of the PI controller will be directly connected to the DC motor. So this is the only block which we will download in the online board. The rest of the block is the simulation model, which will represent your actual DC motor. Before downloading, make sure that you have removed the horizontal arm for your safety purpose. Let's simulate this. So here you can see the response of the simulation model. So the blue line indicates the motion profile output, and the pink one is indicating the motor response. So let me remove one of the extra curve which I've added earlier. So you can see only 2 in the list. We can adjust this response of the motor by opening the parameter block, going to position controller, go to PI controller block, and set the KP as 1. And let's see the response. So now you can see that the simulation model is very closely following the simulation output of the motion profile. So we will perform the same experiment in the hardware. Okay, we will set the PI to 0.1 first and then to 1, so we can see the response of motor in the both manner. So let's go to tools, real-time toolbox, C code generation, select the 20sim template, select the sum model position controller PI which you need to download, say OK. Select the target template as rotary inverted pendulum. So this has an armline board attached to it. So you can see that the board is connected to a LAN network, so it can communicate with the laptop. Say apply, go to connect block. So as this is my previously open project, so you can see the outputs are already connected, but we will do it again. So double click on encoder 1, connect to motor quarter counter. The output is connected to pendulum output of the online board, and compile. Once the compilation is over, you go to command button, click on apply. This model would be running with a discrete time interval of 0.002 seconds or 500 Hertz. But if we download this, we will just executing the model and we won't be able to observe any outputs. To record and observe the outputs, you have to click on this upload with log, and you have to select the variables which you need to log. So I disable all the previous ones so that we can see it again. Yeah, so you can see that no variable selected. So I will record only this one, that is this block encoded to drive motor output, which was our this block. So it will provide the output of this. We will record this output and we'll compare with the simulation results. So we'll record this one, and for this, the sake of comparison, we can also record the motion profile X output. And now we can run this model. So here we can see the setup. So that is the pendulum setup. I have removed the horizontal arm for the safety purpose. You also have to do the same before running this experiment. And now I run this model. So you can see the motor is rotating. And here you can see this is the response which we got in the first simulation output. Okay, so this was the same response we got. Now we tune our PI controller. For this, I go to PI, select the KP and set it to 1. I just click on apply, and now I rerun with logging. So you can see that, so here you can see that this is following very closely to the simulation output. You can save this file as a log of PI, close this and close 4C23. Thank you very much.